So in this video we're going to look at Dmitry Mendeleev and his role in putting together basically the modern periodic table. You may wonder why we're looking at a scientist that lived almost 200 years ago, but the reason is this: it's on the specification. And what I've got here is I've got to just quickly show you a question from an exam paper. This was the Year 10 Progress exam paper at Excel put together right at the very beginning of this specification. And I've got this question here. In 1871, the Russian chemist Dmitry Mendeleev produced the first version of the periodic table. Describe how Mendeleev arranged the elements in this first version. There's 3 marks to this. And this question caught a lot of students out at the time because they hadn't taken possibly this page or two in the workbook seriously. So what we've got here, we've got a little bit of a literacy exercise. It explains exactly what Mendeleev did. No punctuation in that, and you can add that at your leisure. But following that, there's some comprehension questions. All the answers to these were in the passage above, but we'll quickly run through these now because these are quite important. Okay, so just the really salient points now. How did Mendeleev how did Mendeleev order the elements in his table? Well, Mendeleev ordered the elements in his table by increasing atomic mass. So he looked at the atomic mass of all the elements. He puts the lightest one on the very left-hand side, and then he had an increasing row that went up as the elements got heavier. So lightest on the left, heaviest on the right. So he had one very, very long row. After that, he cut his row into segments and dragged the rows underneath each other, forming groups. So how did Mendeleev decide where to cut his row and group his elements? He did it by ensuring that the elements and the compounds of the elements with similar properties were grouped together. Running out of space there. Were grouped together. Okay, so let's be clear about that. So if you look at group 1, for example, I've got a modern periodic table here. Okay, group 1, we've got lithium, sodium and potassium, rubidium, cesium, all in group 1. So what Mendeleev did is we have as we go down, they get increasingly heavier. There's the atomic masses, 7, 23, 39, 85, 133. So they're arranged in order of atomic mass. But he cut his row, so he cut it and dragged the next one underneath. So lithium and sodium and potassium, rubidium and cesium, all those elements have similar properties. They're all metallic, they can all be cut with a knife. They're all incredibly reactive. But it's not just the properties of the elements, he looked at the properties of the compounds. For example, lithium hydroxide is an alkali. Well, he then looked at sodium hydroxide, that's an alkali. He looked at potassium hydroxide, that's an alkali. So it's not just the properties of the elements that are similar, it's the properties of the compounds that are similar. Okay, so it's the properties of the elements and the properties of the compounds. So that's one way Mendeleev grouped his elements, the elements and the compounds of the elements with similar properties were grouped together. And also number 2, let's put number 2 over here now. So let's just back like that. Number 2, he left gaps. So Mendeleev lived at a time when not all the elements had been discovered, and he recognised that. He thought, well, we probably haven't discovered all the elements, so he left gaps for yet to be discovered elements. Yet to be discovered elements. Okay, what made other scientists trust Mendeleev's table of the elements? Well, when Mendeleev first came up with his periodic table, other scientists said, I don't really believe that. It looks very nice, I can understand what you're doing, but it's surely just a coincidence. And so they didn't trust him. But what Mendeleev did, he left these gaps for yet to be discovered elements. He didn't just leave gaps, he predicted that they would be discovered, and he predicted what their properties would be, and he predicted what the properties of their compounds would be. And so it says at the bottom here, the discovery of gallium in 1875. The discovery of gallium in 1875. I don't think you need to learn the date or things, or even maybe the elements. You just need to know that elements were then discovered. Mendeleev correctly predicted its properties. And the properties of its compounds. Okay, next page. Look carefully at the periodic table, the modern periodic table. The elements are not arranged in order of atomic mass. What are they arranged in? Well, they're not arranged in atomic mass. On the modern periodic table, they're arranged in order of atomic number. The atomic number is the proton number. They're arranged in order of number of protons. So the element with the smallest number of protons is top left. Okay, here, hydrogen. And then we go across the row, as Mendeleev came with a huge row, and the next one has 2 protons. And so the protons go up 1 each time. Now remember, Mendeleev cut the row and put the elements with similar properties underneath each other. So the row was cut here, and then the next row was dragged all the way over here to lithium. Okay, it has 3 protons, 4, so it reads like a book, left to right. 5, 6, 7, 8, 9, 10 neon. And then just the same way as read a book, we go to the left-hand side, next row here, sodium 11. So the modern periodic table is arranged in order of protons. This bottom number, it's not the top number, it's the bottom number. And we've got a key here that tells us that. The element name at the bottom, we've got the atomic number, the number of protons. So that is how the modern periodic table is arranged. Okay, so look at group 6 and 7, find a pair of elements that would be in the wrong places if they're arranged in order of atomic mass. So Mendeleev arranged in order of atomic mass. Now if we look here, here's group 6, because groups go down the periodic table, group 6, and there's group 7. So if we look here at tellurium and iodine. Now Mendeleev arranged in order of atomic mass. Now tellurium has got an atomic mass of 128. Iodine comes after it in the row. And so it has an atomic mass of 127. Now, if this were Mendeleev's first draft, he would have had iodine here and tellurium here. It would have gone 122, 127, 128, 131. This breaks Mendeleev's rule. Now, Mendeleev was clever enough to realise that iodine had the same properties of bromine, chlorine, fluorine, and not the elements in this group. So Mendeleev broke his rule with iodine and tellurium, and this is just another reason other scientists didn't believe him, because they said, Mendeleev, you're breaking your rules, you reversed iodine and tellurium. But Mendeleev said, yeah, because iodine has the same properties as these guys. So these two have been reversed. But if you look at the atomic numbers, tellurium has got 52 protons, iodine's got 53 protons. Okay, so the modern periodic table is arranged in order of atomic number, and this obeys the rules now. Okay, so group 6 and 7, so it's iodine and tellurium. Why is it possible for an element? With a high atomic number to have a mass number that is lower? Well, it's all down to number of neutrons. Okay, so different numbers of neutrons. If you go back to a few pages, and when we looked at the relative masses of different subatomic particles, neutrons had a mass of 1 and protons had a mass of 1, different numbers of neutrons. Okay, so if we look at this, so if we look at the periodic table here, we can see that it's possible for iodine to be after tellurium, even though it has an atomic mass that's less, because it has different numbers of neutrons. So it says here we've got iodine's got 53 protons. Well, iodine has got, if you take these two numbers apart, you can calculate the number of neutrons. It's got 127 minus 53 is 74 neutrons. Okay, whereas if we do the same here, 128 minus 52 protons for tellurium, it gives us 76. So you can see that tellurium has got two more neutrons than iodine, which makes its atomic mass heavier, than that of iodine. Even though iodine's got one more proton, it's got 2 less neutrons. So that's why the atomic mass of iodine is lower, because it has less neutrons. Different numbers of neutrons. Iodine has 2 less neutrons, and you can write that into more detail if you want. Last thing I want to look at is just a couple of very, very basics of the periodic table. Now these are absolutely critical. So draw and label on the outline of the periodic table below where the metal, non-metal divide is. I do not want you to label all the elements in here. That's not what this is about. If we look at all the elements on the periodic table, they can be divided into one of 2 different families, metals and non-metals. Now the metals live on the left-hand side and the non-metals live on the right-hand side, and there is a very, very clear dividing line, and you need to know it. It starts here. That's where it starts. You can bring it across like that if you want to, because hydrogen is in the non-metal side as well. That's a gas. But this dividing line, it steps down a bit at a time, like this, like a set of stairs, goes down like so. Okay? Now, the non-metals are this side, non-metals. Okay, and the metals are this side. Now, it's absolutely crucial that you know that. Hydrogen is a non-metal as well. That it just sits a little bit separate to this group. Okay, but that's the dividing line for metals, non-metals. Also on the outline above, can you clearly label the group numbers and period numbers? We said it a moment ago, just up there. Groups go down, so groups go down. So this is group 1, all these. This is group 2, so groups go down. So these are groups. Group 1, group 2. This is group 3, 4, 5, 6, 7, and you may be thinking this one's called 8. It's not, it's called group 0, okay? I always say, because these are the noble gases, okay? Helium, neon, argon, krypton, xenon, and radon. These are the noble gases, okay? The noble gases are famous because they react with absolutely nothing. And that's why I can sometimes ask students to remember it's called group 0, because these react with absolutely nothing. Okay, so these are our group numbers. Now, period numbers. If groups go down, periods go across. Periods go across. So this is period 1 at the top here. And period 1 is the one students always forget, because it only contains hydrogen and helium. It only has 2 elements in that one. This is period 2. This is period 3. Okay, and it's the examiner's absolute favourite question to name an element in period 2. Okay, and students will always pick one from this row here. Okay. And it's the examiner's absolute favourite question because students always forget period 1. Period 1's hydrogen, helium. So period 2 is this row here. It was a mock exam for my group in the mock exam for my groups last year. I snuck that question in there, and every single one of these kids, and loads of them got grade 8s and 9s. Every single one of these kids picked an element for period for period 2 from period 3. So yeah, don't forget the first one. So that's period 4. This one here. 5, 6. You get the idea? So, are groups horizontal or vertical? Groups are vertical. Periods are horizontal. Do elements in the same groups or periods have similar properties? Well, Mendeleev arranged elements with the same properties and the properties of their compounds in groups. Okay, in groups. Okay, elements in the same period have nothing in common at all. And there's an introduction to Mendeleev and the periodic table.